Okay, welcome to the second session of Wednesday, second session on environment. And I'm your moderator, Karen Laley. And so the first talk is a 30 plus 10-minute talk by Roderik Overzier. And so Roderik, if you can go ahead and share your screen.
How does this look?
It looks fine. We can see your slides. So
Okay, so let me start by thanking the organizers and all participants really for putting together this wonderful conference. This is a review talk. I tried to be thorough in my referencing, but I'm sure I missed all kinds of interesting work. So feel free to add any references to the Slack thread related to this talk. So I'd like to start with putting up this rather simplistic picture of what the first giga year of the universe roughly looks like, at least in my mind. And that is that any kind of structure that we're interested in ultimately starts with a cosmic overdensity on some scale. If it's a large scale overdensity, then such a region will become a galaxy cluster. More modest overdensities will form the first galaxies. And if it's a really high overdensity on an extremely small scale, then this will form supermassive black holes that we need to power quasars. And we also know that all these types of structures have some contribution to reionization. And since we're here talking about structures that are some of the first structures to form in the universe, they're bound to create early reionized regions in the universe. And we also know that we need some kind of seeding mechanism for the supermassive black holes. Whether your favorite black hole seed formation scenario are population 3 stars or more massive direct collapse black holes, these formation scenarios are also closely connected to cosmic overdensities. So in the first part of this review, I will walk this upper path relating overdensities to galaxy clusters and a little bit of reionization. And then in the second part, I will walk this this path related to the black hole, so that we can really try to compare the two. Now, theory tells us that galaxies in the most massive dark matter halos today formed their stars at very high redshifts on average. And if you focus on today's massive clusters, let's say halos of 10 to the 14 to 10 to the 15 solar masses, most of their action is over by the time you get to redshift 2. So this figure here from Overzier et al. Shows very nicely that the peak star formation epoch for the galaxies that make up these kind of structures today happens at redshift 3, 4, 5, etc. So that's theory. And we also see this if we look at some rather extreme examples of galaxy clusters that have been found at very high redshifts. So here example redshift 1.2, redshift 1.8, and redshift 1.98. And these particular clusters, despite their high redshifts, they already have a lot of the features that we know and love about galaxy clusters, such as a thermalized ICM and a very high fraction of passive and early type galaxies. In particular, the cluster at redshift 1.98, the estimated formation redshift of the stars that make up the passive population in this cluster, according to Willis et al. 2020, should be placed somewhere around redshift 10. In other words, long before this object became a cluster. Currently, the most distant cluster discovered is probably this one at a redshift of 2.5. In the Cosmos field, there is a large agglomerate of structures between redshift 2.4 and 2.5 that is referred to as Hyperion. And the largest substructure within this structure is this object here that has an X-ray luminosity of 10 to the 44 erg per second, possibly a virialized mass of 10 to the 14 solar masses. It would evolve into a 10 to the 15 solar mass cluster by the present day. However, we need to be a little bit cautious with the interpretation of this this X-ray structure, because the structure contains several radio AGN. So there's some ambiguity here. Nonetheless, it's a very old, impressive, massive structure. This figure here summarizes what especially Sunyaev-Sadovitz surveys have contributed to the field of cluster evolution. Planck, SPT, and ACT have drastically increased the sample of galaxy clusters out to redshifts about 2. But it also shows you the limit of these techniques. And we essentially fail to go much beyond redshift 2, not only because of technical reasons, but mostly because of astrophysical reasons. And that is because if you look at the typical growth of, let's say, a massive cluster like a coma, or proto-coma cluster in this case, and you look when such an object first passes this magical 10 to the 14 solar mass threshold that we use to define clusters, then this happens to a redshift of about 2. So we do not expect any clusters or highly massive dark matter halos much beyond redshift 2. So does that mean that the study of cluster formation or evolution ends there at redshift 2? Well, no. So if we all put on our dark matter glasses for a minute and we look up to the sky, we would actually very easily be able to pick out the regions where massive objects are forming. And you can see this by comparing these two snapshots from the Millennium 2 simulation, redshift 6 and redshift 0, showing you 3 different scales. And if we could see the dark matter, it would be quite easy to point out where we believe the clusters are forming. Now, I don't have dark matter glasses, but mixed in with the dark matter, there would be gas and galaxies, and those we can try to detect. Again, this works in theory and in simulations. We see there very clearly that higher mass clusters today generally came from larger overdensities of gas and galaxies. And we can try to detect those, and we can even predict some interesting physical parameters like a present-day cluster mass from a galaxy overdensity or a gas overdensity measured at very high redshifts. And so in principle, this would allow us to follow cluster evolution way beyond redshift 2, perhaps all the way into the epoch of reionization. So that theory, does it work in practice? It does. Cluster progenitor systems have been found out to very high redshifts. And these systems, they generally satisfy the properties that we expect for the protocluster stage of clusters, again, according to simulations. And here I show you 2 examples. These were some of the first structures discovered. The so-called spiderweb protocluster at redshift 2.2 and the SSA22 structure at redshift 3. Despite the redshift of the SSA22 being higher than that of the spiderweb, it seems that the SSA22 structure is actually much more impressive structure, a progenitor of a very massive cluster. So in the last 2 decades or so, maybe 30 or 40 of such systems have been found in all kinds of ways by targeting quasars, radio galaxies, or serendipitously in the field. And in the past 5 years, I would say that this has completely changed. And we now have samples of hundreds to even thousands of candidates of such structures, largely thanks due to the very wide and deep surveys on 8-meter telescopes. And actually the main limiting factor at this moment seems to be the spectroscopic follow-up to confirm all these large numbers of candidates. And some of the projects and surveys that have been particularly helpful in this explosion of interesting structures at high redshift are the Carla project, which was a project to target radio loud objects at high redshift and look for their environments. the HyperSupremeCam systematic survey in broad and narrow bands that I highlighted here. And also a very nice surprise has been the discovery of these massive systems in surveys with Planck, South Pole Telescope, and Herschel. So I'll highlight some new developments or recent developments in this area. One of these, as I mentioned, is the Subaru HyperSupremeCam systematic survey, and in particular the wide survey allowed us to select 200 candidates of these systems at Redshift 4 using only 10% of the initial survey data. And we believe that these systems have the properties typical of sort of intermediate mass clusters today. And if you have such a large number of candidate systems, that means you can make all kinds of interesting stacks and statistical exercises that we couldn't do before, such as this result by Mariko Kubo et al. 2019 that show that these UV selected Redshift 4 systems are detected in a deep stack of Planck data. And so this shows that despite their UV selection, there's probably also a large obscured star formation rate with some AGN activity mixed in these systems at Redshift 4. Now, another very positive addition to this field has been the dense spectroscopic field surveys, such as the VMOS Ultra Deep Survey, VUDS. And this project showed that if you take densely sampled spectra on some sky region, then you're also able to find these kind of structures in redshift space without necessarily being able to detect them in terms of a surface overdensity in a sky plot, as shown here in these two figures. And then a third very interesting addition to this area of research has been the IGM tomography studies, such as the Mammoth, Clamato, and Lattice projects. And this has really opened the door to not use galaxies to select these kind of structures, but to go after the gas overdensities. And in this case, these structures are discovered through the absorption features that they imprint on the spectra of background quasars and galaxies. And within a couple of years, we'll have two new instruments, VLT Moons and Subaru PFS, that will be absolutely fantastic to combine all of these search techniques over very large areas in a systematic way. Another very interesting development has been the realization that we can use CMB and SZ surveys to look for these overdensities of obscured star-forming galaxies, which leads to so-called cold spots in CMB data. And here I show two quite spectacular examples of systems with Redshift 4 and 4.3 that have received a lot of attention in recent years. These structures appear to be far infrared bright, but UV dark. So perhaps they are complementary to our UV selection. In both cases here, there is a large number of galaxies on rather compact scales of maybe a few hundred kiloparsecs, leading people to believe that perhaps we're seeing here the proto-BCGs. And on large scales, these systems appear to be rather overdense and massive, leading to the conclusion that perhaps these are super coma clusters in formation, as you can see here in this overview produced by Long et al. 2020. Now we finally get to the first billion years, which is the point where I wanted to get to. So in theory, we can extend this kind of search for cluster progenitors all the way into the epoch of reionization. In this work from Chang et al. 2017, it is shown that actually, since these systems are so biased, they form rather early, they contain large numbers of star-forming galaxies distributed over large co-moving volumes. And that means that they actually make a non-negligible contribution to the overall cosmic star formation rate density. And based on the simulation, perhaps they could contribute as much as 50% of the cosmic star formation rate density by the time you get to redshift 10. And so these kind of structures could be major sources of in particular, the early reionization. And maybe if we had maps that show the topology of the reionization process, this could be dominated by these very large bubbles surrounding these first major structures. Again, this is all theory. Does it work in practice? Well, actually, we have many examples now of such structures, mostly composed of Lyman break galaxies, Lyman alpha emitters at redshift 6 to 7. This morning, we saw the talk by Wei-Da Hu giving an example at redshift 7.1. And so there's certainly no lack of rather rich structures that we can detect. Actually, with quite modest means, using dropout surveys, Lyman alpha narrowbands, followed by spectroscopy. And these are some of the best examples that I know of, but there are others. And we've also heard during this this conference that things like double peak Lyman alpha emission or enhanced Lyman alpha transmissivity may be smoking guns of large-scale ionized bubbles. And if that is true, then perhaps we may expect that in and around these first examples of overdense regions, such tracers of reionization will be detected in the coming years and at a rate that is more common or higher than around typical field galaxies at a similar redshift. And there are several observational papers that I have referenced here below that seem to go in toward this direction with indications that there might be observational signatures of these first large overdense regions. Okay, now we finally get to the quasars. So we have heard many times during this conference that theory and simulations consistently predict that the first quasars form in early overdense regions. And we've seen evidence that some quasars indeed appear to be in rather complex or dense environments. However, as I will show and others have shown, this does not appear to be the case for the population of the first quasars in general, given the current observational evidence. And this becomes particularly striking when we compare these objects with the other massive structures known at redshift 6 to 7 that I have just showed you. So let's start with making a very quick summary of what we think we know about the redshift 6 quasar population. The typical black hole masses are 1 to a few times 10 to the 9 solar masses. Dynamical mass estimates suggest that the mass to black hole mass ratio is about 7 times below the local M sigma relation. So this is one of the methods that we can use to try to infer dark matter halo mass. I know of at least 4 or 5 more or less independent means of estimating the halo mass of these redshift 6 and 7 quasars, using proximity zones, arguments based on the number density, direct comparison with simulations. And I think these all point to halo masses of around 10 to the 12 to the 12.5 solar masses. We've also seen that some quasars require superhuman growth, in particular the more massive black holes above redshift 7. And what I mean by superhuman is that no human can currently explain the formation of these objects without invoking some kind of exotic scenario that gives us, for example, a 1,000 solar mass black hole at a redshift of 50 that then also needs to accrete continuously at the Eddington rate. And we also know that 10 to the 15 solar mass clusters today typically had a halo mass or had a halo with a mass of somewhere around 10 to the 12 solar masses way back in their merger history, somewhere around redshift 6. So the naive expectation of all of this is that the quasar environments at redshift 6 and above should be incredibly rich. So let's ask if they are. I've taken this list from a paper by Chiara Mazzucchelli from 2017, and I added more recent papers. Feiger Wang showed a similar overview with sort of a classification of whether these particular quasars show evidence for overdensities or not. And I'm actually going to take a little bit more conservative approach than Feiger Wang did, and that is only allowing spectroscopic evidence for overdensities. Okay, and the reason for this is twofold. We have seen many times in the past that photometric overdensities of dropouts later were shown to be projection effects after doing spectroscopy, but also all the protocluster systems that I showed you that we know of at redshift 6 and 7, they have all been confirmed spectroscopically. Okay, so so if we do that, then this list looks rather sad. If we had made this list 2 years ago, we would have answered no everywhere. Recently, there have been a number of very interesting papers that we've also seen already appearing in this conference, presenting evidence for overdensities on some scale with some selection method for at least a number of quasars, but certainly it seems to be the minority at this point. One of these is this object, 0836 at redshift 5.8, discovered by Xiaoyi Fan et al. 2001. It has a black hole mass of about 3 × 10⁹ solar masses. This object formed one of the chapters of my PhD thesis 15 years ago, and we presented there a photometric overdensity of 7 dropouts. I've been highly skeptical of that result for 15 years because of the lack of spectroscopic confirmation, as I mentioned, until about a year ago when a very interesting paper appeared led by Sarah Bosman that obtained 3 redshifts of galaxies close to the quasar, 2 of which are coinciding with the dropout galaxies. One of these objects, which is Galaxy A, is actually detected with Spitzer at 3.6 micron, which we already knew in 2009 when we obtained the Spitzer data, but we didn't have a redshift, so we couldn't make too much of it. But now we know that this means that this is an object with a stellar mass of a few times 10 to the 10. The inferred halo mass would be 10 to the 12 solar masses, and that would suggest that this field does not contain just one massive 10 to the 12 solar mass halo associated with the quasar, but at least one more associated with one of these galaxies. And this requires an overdensity of on this scale and of this type of halos of about 20. Another interesting object, which curiously enough was also from the sample of 3 objects discovered by Fan et al. In 2001. This is a quasar redshift 6.3. We have seen this figure several times already during the conference. In this case, there are six spectroscopically confirmed galaxies. And although these 2 fields differ in the details, I would actually argue that actually on scales of about 5 proper megaparsec radius from the quasar, they are quite similar, as shown by these 2 projections here. Now, there are other interesting environmental finds that we have also seen presented during this conference, such as the companions, very close by massive companions detected in C2, or the recent result of a first binary quasar at redshift 5.7 by Yu et al. And so this could either reflect maybe the duty cycle of typical merging activity in a rather uniform quasar population, but perhaps it could also be an indication that the redshift 6 quasar population is more pluriform than previously thought. And that perhaps could explain some of these very striking differences. Now, the reason why I showed you all this evidence on non-quasar related overdensities at redshift 6 and 7 is because now we can then compare what has been found around the quasars to these other so-called protoclusters. And what we then find is that perhaps the structures as found, for example, around these 2 quasars, 0836 and 1030, they resemble sort of the densest peaks that you find inside these redshift 6 to 7 protoclusters. but they appear to lack the large-scale structures that are typical only of these protoclusters. And I think this is a very interesting clue, perhaps, to what is happening.
5 minutes.
So, thank you. So let's look at some possible solutions or explanations that could be consistent with these data. So the first often heard conclusion is that the quasars are in dense environments, but for some reason we are not detecting these environments. And so the main problems to me is that this would imply a rather strange luminosity function for galaxies in the vicinity of the QSO, but actually out to tens of megaparsecs. And it is also conflicting with the overwhelming evidence of very large overdense structures in the field that were quite easily found, as I have shown you. So another common explanation is that the quasars are in dense environments, but photoheating has suppressed star formation. And the main problems here I see is that actually the best evidence for companions of quasars today is on very small scales and not on large scales. It would also require that this photoheating is efficient out to many megaparsecs, uniformly over 4 pi steradian, and also that the quasar duty cycle needs to be close to 1 in order to continuously suppress any Lyman alpha or Lyman break, Lyman alpha emitter or Lyman break galaxy formation over very long time scales. And actually, one of the results from the paper by Sarah Bosman et al. Shown here in this in the bottom right is this object found very close to the quasar redshift 5.8, which shows very bright double peak Lyman alpha emission. So clearly, this galaxy was able to form within the ionization cone of the quasar. But what's more, the ionized region actually allowed this double peaked, this very strong double peak Lyman alpha emission to emerge. And so, if anything, this quasar ionization makes it easier to spot these objects. And so these two particular explanations have never been very convincing to me. And a third option here that I'd like to maybe put back on the table is that the quasars might be in dense local environments, but not necessarily the largest, the most massive, the most extreme overdensities that we usually associate them with. And I'd like to bring back to your memories these results from already 10 years ago. And that is, if we look at the merger history of massive clusters selected at redshift 0, then those objects are likely to include 10 to the 12 or more massive solar mass halos at redshift 6. But that's not the experiment we're doing here when we're selecting quasars, okay? So if we look at what are the typical descendants of 10 to the 12 solar mass halos selected at redshift 6, then their descendants at redshift 0 are much more diverse, spanning maybe 2 orders of magnitude between 10 to the 13 and 10 to the 15 solar masses. No doubt massive structures, but certainly not necessarily the largest. And there's another interesting paper here shown on the right from Angulo et al. 2012 that actually shows you that it is the large-scale environment, scales of tens of co-moving megaparsecs, that is most indicative of the future growth potential of a structure selected at redshift 6. And in these particular simulations, if you select the most massive object at redshift 6, it does not become the most massive object at redshift 0. On average, actually it becomes less massive than structures that are not as impressive yet at redshift 6. Now, the final topic I'd like to reach here is related to the seeds of the first supermassive black holes. So this question of environment has direct relevance to many of the black hole seed formation and growth scenarios proposed. The direct collapsed black hole seeds have been postulated in order to explain the supermassive black holes above redshift 7, but they have never been detected, and we don't know whether a viable formation scenario exists. According to the theory for the formation of these very massive seeds, we need a combination of an enhanced local UV photon background together with high merger rates of mini halos. And interestingly, these are predicted to primarily occur in very large overdensities above redshift 10. So quasars like 089836 and 1030 could be good examples of regions in the early universe where such direct collapse black hole formation was stimulated. And I would expect that quasars like ULAS 1342 at redshift 7.5 may show similar results. This is my final slide. Faiga Wang already presented to you a very interesting overview of all the interesting JWST programs that are going to address these issues related to quasar environments. I'd like to add to that several programs in GO and GTO time that will target radio loud galaxies between redshift 4 and 6, and that will offer us a very interesting comparison in terms of the host galaxies and environments with the quasars. Moons and PFS will soon begin to systematically study large-scale environments. And I'd also like to mention that instruments proposed for GMT and ELT are actually very well matched to the typical structure sizes of what we need to do this really, really well spectroscopically. And I think I'll conclude here. There are some other ways in which in the coming years we will learn a lot more about black hole demographics that will maybe help us to at least indirectly infer much more about the seed population, if not detecting them directly. Thank you very much.
Thank you for a very informative talk. So we have one question up on the Q&A from Sheila Kanapan. Is the mix of environments for quasars statistically consistent with random environments?
I think that could very well be, yes. Of course, the other side of the coin is that the 3 or 4 objects that have, several confirmed companions nearby, I think that this is quite spectacular. Even confirming a small number of Lyman alpha emitters at the same redshift as the quasars. This is not something that you see in typical, let's say, field environments. But yeah, I personally believe it's quite possible that we're seeing a very large mix of environments, which probably is no longer true by the time you get to redshift 4. Yeah, I agree with that.
Okay, great. Are there any other questions? There's no other open questions on the Q&A. So while we're waiting for that, maybe this is not my field, but I'll ask you a sort of general question. What do you think is the most pressing open problem in this field today that can be addressed today? How about, and we don't have to wait for any new machines.
Well,
Okay.
until you added the last sentence, I would say I would be really interested in finally knowing what's the seed population. I think this this is the elephant in the room. Knowing whether we have to start from population tree seeds or from much more massive seeds would create enormous clarity by discarding a whole family of models. And this is what I would really like to know. I'm hopeful that maybe not now, but within the next 2 years, especially the many JWST programs, we will learn a lot more about this.
Okay. We have a question from Darren Croton. Didn't we just see that higher Z quasars were much more clustered, so not random?
Yes, so I should maybe stress that what I presented here really refers to the redshift 6 and higher quasar population. We have not measured a correlation function for quasars or redshifts at these redshifts. And so I agree with most of or everything that Christina presented this morning. But all those constraints on clustering, cross-clustering, all comes from redshifts 4 and lower.
Great, we still have time. So we have another question from Michael Strauss. We heard intriguing evidence in earlier talks that overdensities around z equals 6 quasars were more prominent in obscured galaxies than in unobscured quasars. Do you find this convincing? How does that fit within your scenario?
So thank you very much, Michael. I was expecting this question. So of course we often make the argument that somehow we are convinced that the massive structures are there, but we are not detecting them. Therefore, all these galaxies are obscured. Okay, it is certainly possible, but I don't find it a very convincing argument. It sounds a little bit to me as the epicycles. Now, if this were at redshift 4, I would certainly I would have no problem with this. And I've shown you examples of these massive protoclusters that are primarily seen in a dust obscured way, lacking many UV of any UV galaxies, UV selected galaxies, Lyman alpha galaxies. Above redshift 6, I'm not convinced. I find it too easy to say, well, the structures must be there. We're just not seeing them, just in order to hang on to our strong conviction that these quasars must be in the most overdense regions of the universe. I'm happy to be proven wrong, but I don't think we have, there's convincing information to take this as our explanation. So,
Okay, so we have another question by George Gonzalez Lopez. If the QSOs do not live in the largest overdensity structures, should we be looking for other sources such as sub-millimeter galaxies at z greater than 6 to find the most massive halos?
So that's a good question. So that allows me to say it a little bit more clearly. I do believe that the quasars are in very massive halos, possibly the most massive halos that you find at redshift 6. But these are not necessarily in the largest overdensities on tens of megaparsec scales. So maybe it is possible that by selecting these very early collapsed objects, such as the supermassive black holes and the quasar hosts, we are sort of biasing ourselves to overdensities that were very large on small scales, not necessarily on large scales.
And there was an addendum to Michael Strauss's question. Sorry, I mistyped. Unobscured quasars should be unobscured galaxies. So that was what he was thinking, rather than quasars. Oh, I lost the question. I'm not sure where it is. Here it is. But still a couple minutes. Anybody have another question? I guess I will ask another vague question. So what are you currently working on? What is currently the most exciting project you're working on?
Good question. One thing I'm really intrigued by is the role that these overdense structures can play in the early reionization process, and whether this can be detected rather than saying, look, we find a large overdensity of galaxies at some redshift, and therefore probably this region reionized early. It would be really nice to be able to show this observationally, and I think there are ways in which this can be done very soon by measuring, for example, the escape fraction of Lyman continuum photons coming from these regions, and compare this to galaxies in the field.
Okay, let's see. I don't know if this can be done in a minute, which is all we have left. Perhaps so. Reversing the argument, what is your idea regarding not detecting AGN QSOs in, for example, the many serendipitously found Z 6 to 7 overdensities of galaxies you summarized?
Yeah, that's another good point. So I should have said that, as far as I know, none of these structures contain luminous quasars. Of course, it is possible they contain obscured quasars, or there are supermassive black holes, but they're currently not actively shining. So I don't see this as a problem. It is easy to switch off a quasar in a large-scale structure at some moment in time. However, it is impossible to switch off the large-scale structure around an object that is currently a quasar. And so I think that there's a lot of information in this kind of comparison.
All right, well, let's move on to the next talk, which is by Laura Keating. Okay,
Yeah,
Laura,
great.
we hear you, we see your slides, and so I think you're ready to go.
Okay, great. So yeah, thank you very much for giving me the opportunity to speak today. And I'm going to tell you about some of the work I've been doing trying to model the smallest quasar proximity zones in a case where the light coming from the quasar can flicker on and off. So first of all, what is a proximity zone? Well, if we look at a spectrum of a high redshift quasar, this one is at redshift 6, the red dashed line there represents the Lyman alpha emission peak, and blueward of that we see the Lyman alpha forest. And at this redshift, most of the Lyman alpha forest is saturated due to the high neutral fraction of gas in the intergalactic medium. But if you look close to the Lyman alpha emission peak, you do see quite a lot of transmitted flux. And this is because the ionizing photons coming from the quasar itself can ionize the gas in the immediate vicinity of the quasar, allowing for flux to be transmitted. And this region is known as the quasar proximity zone. And why would you be interested in these proximity zones? Well, in one case, they tell you about something about how long that quasar has been shining for. So what's shown in this plot here on the y-axis is the quasar proximity zone radius, and on the x-axis is the quasar lifetime. And the gray contours here are results from a cosmological simulation that's been post-processed with a radiative transfer code, assuming the quasar always shines at a constant luminosity. This is from a paper by Christina Eilers. And you basically see two phases of the proximity zone growth. Initially, you see a strong correlation between the proximity zone radius and the quasar lifetime, because you essentially have a strong gun sphere expanding out into the intergalactic medium. And then eventually you reach this equilibrium value, where the proximity zone size no longer really depends so strongly on the lifetime. And this is because you have a balance between the ionizing flux of the quasar and the ionizing background of the intergalactic medium. So by comparing a measured proximity zone size, which is the red line shown here, with the results from these simulations, you can infer a lifetime for this quasar, in this case, just over 10 to the 3 years. So this is an interesting measurement of how long these quasars have been shining for. And there's a nice sample of these observed proximity zone sizes. So now I'm plotting quasar lifetime against the quasar proximity zone size against the quasar magnitude. And the different colors of the points here represent the redshift of the object. And if I now plot this equilibrium proximity zone size that I talked about before, you see that a lot of the quasars do cluster around this value, but there are some that are quite far away from it. And there's been an increasing number of objects observed to have these small quasar proximity zone sizes. So you see there's quite a substantial population of them now. And this is a biased sample that's plotted here because these objects are specifically targeted for follow-up. But you can estimate that about 5 to 10% of quasars in this redshift range do have these small proximity zones. And so is this maybe a population of young quasars that have lifetimes of 10 to the 3 to 10 to the 4 years? And if so, is that compatible with being able to grow a 10 to the 9 solar mass black hole by redshift 6? So how can we explain this? So one thing that has been investigated already by Fred Davies is what if the quasar source isn't constant? What if it flickers on and off? So here in this movie, I'm showing an example of a quasar that's on all the time. In the top panel here, I'm showing the luminosity as a function of time. And the black line is a black dashed line is the constant source. And the blue line is a source that's flickering on and off. In the second panel, I show the results of how this affects the neutral hydrogen fraction in the intergalactic medium around the quasar, which would be around redshift 5.92. And you can see in the black dashed line, so the constant source, the gas is always highly ionized. But if the source can turn on and off, you have these two phases, either being highly ionized or it can recombine when there's no ionizing photons. And this also has an effect on the Lyman alpha forest, as shown in the third panel. Again, in this time when the source is always constant, we see that the quasar spectrum always looks the same. Whereas if the source turns on and off, then we can either have a lot of transmitted flux when the gas is ionized or hardly any when it's had time to recombine. And this is also reflected in this proximity zone size. When there's no transmitted flux in the quasar spectrum, you see a small proximity zone size. But when there's a lot of transmitted flux, you get a larger proximity zone. And this oscillates in the same way that the luminosity oscillates, so they're strongly correlated. And so that's kind of work that's already been done, but I want to try and bring something new to this today. And so what I'm trying to do is to link results from cosmological simulations where these massive black holes are grown with these proximity zone sizes to see, can we reconcile these two values, these small proximity zones and also these massive black holes. So I've been working with Thiago Costa from MPA, who's an expert in running cosmological zoom simulations of the environments of these black holes. And what's shown here is an example of one of the simulations. So in the larger panel, you can see that the cosmological environment is captured, both the large scale inflows and the outflows. But the resolution of these simulations is very high. So if you zoom into the center, you can see that the vicinity around the black hole is also really well resolved. And if we look at the black hole masses that are found in these simulations as a function of redshift, the different simulations are the colored lines. So they're all ending up with black hole masses are slightly above 10 to the 9 solar masses by redshift 6. And this is nicely compatible with the observed black holes, which are shown as the black solid points. And as I already said, these simulations have a high spatial resolution. And so that translates into a high temporal resolution that we can extract these quasar light curves from and apply them to our radiative transfer code to model the quasar proximity zones. And so this is an example. Okay, this is an example of how these light curves look extracted from the simulations and applied to the intergalactic medium. So in the top panel, you see the magnitude, which can vary by several orders of magnitude, depending on the exact time. You see again, and as we saw before with a simple source turning on and off, this has a resulting effect on both the neutral hydrogen fraction and the Lyman alpha forest flux. And finally, in the bottom panel, we show the effect this has on the quasar proximity zone size. And again, we see that it can change depending on the current magnitude of the quasar. So if I take the results from this movie and I just compare them to the observations, so the black points here are the observations and the orange points are what I just showed. And again, this black solid line is this equilibrium proximity zone size. You can see that there's times when simulations are well away from equilibrium. And this is when the quasar magnitude has just changed suddenly and the intergalactic medium hasn't had yet time to respond to this change. So the proximity zone and the IGM are no longer in equilibrium. I can also add in results from some other sightlines that have been post-processed with other quasar light curves. And so each color here is just a different sightline and every point is different time sampling. And you can see you really nicely start to fill out the space between the quasar proximity zone size and magnitude, even just from a handful of sightlines. And so the take-home message of this is by using these flickering AGN light curves that have been shown in simulations to grow 10 to the 9 mass black holes, you can get a population of small proximity zones, although perhaps not quite as many as observed. And in this case, it's just a signature that the quasar has recently changed its magnitude suddenly, and the IGM hasn't had yet time to respond. So thank you.
Very interesting talk. We have a question from Michael Strauss. Can you explain further why the inferred proximity zone size flips between two values, that is, has a bimodal distribution as the quasar flickers? Why don't you get intermediate values?
Yeah, so the recombination time of the IGM is quite short at these photoionization rates. So you quickly, you kind of end up, you quickly change from one value to the other. And in this case, maybe it's actually clearer with the other movie. In this case, there's an absorber that's kind of close to the quasar. And so it can be either highly ionized when the quasar is fully on, so you get a larger proximity zone size. But once the gas had had some time to recombine, your proximity zone size will end there. Now, this is just for kind of the specific sightline and also the specific light curve. You could also have longer breaks that will further allow the gas to recombine more fully, and this would give you other values. So it kind of depends exactly which sightlines you're looking for. As I said, I've only applied this to kind of a handful of sightlines.
Okay, so I think in the interest, there's another question, but in the interest of time, I think we will, to stay on schedule, we'll send that to the Slack. So let's see if Jaclyn Champagne can share her screen.
Okay, you can hear me okay?
Yes, I can.
Okay. And you can see?
Yes.
Okay, great. Start my timer so I don't go over time. Okay, hi everyone. I'm Jackie. I am a finishing PhD student at the University of Texas at Austin, where I have primarily worked with Caitlin Casey, but I have also collaborated with a number of the people at this conference, especially at MPIA. So I will be talking about a search for enhanced galaxy evolution in the environments of Redshift 6 quasars using a couple of different tracers. So many of my introduction plots you have already seen throughout this conference, so I will give a very brief review of them, which is great. That leaves me more time for results. So I am most interested in finding these early galaxy protoclusters, and the two things to really keep in mind from simulations and what they predict for protoclusters is that they are very spatially extended overdensities at early times. So the most massive protoclusters can span, over a ½ degree on the sky in these sort of like filamentary structures that are not varialized to a single bound halo. And another thing is that they contribute non-negligibly to the total cosmic star formation rate density, especially at redshift 6 and 7. So that kind of leads us to the conclusion that we should be looking for enhanced star formation on megaparsec scales. So how do we identify protoclusters in the redshift greater than 1 universe? Here I'm showing a schematic from Roderik's protocluster review paper, which is already a little bit outdated in terms of confirmed protoclusters that we do have, but compared to galaxy clusters, these things are very rare. So how are we finding them? If we're just blindly looking for these evolving structures, it makes the most sense to identify them as overdensities of star-forming galaxies. So occasionally these are found serendipitously in the redshift distribution of galaxies like Lyman alpha emitters or H alpha emitters or dusty star forming galaxies when they're followed up spectroscopically. But in the context of this conference, massive galaxies are a good place to start to look for nearby protocluster signatures, because we know that they're residing in already massive halos at early times. So historically, that has basically been massive radio galaxies and quasar galaxies, generally through targeted narrowband imaging, or kind of found as these surface overdensities in these, wide field narrowband imaging surveys, or follow up of these unresolved sources in something like Herschel or Scuba 2. But quasars give us a really good starting point, because we know that they host supermassive black holes on the order of 1 billion solar masses. And theoretically, of course, we have been debating this throughout the conference, they could reside in the rarest and most massive halos. And we've also been hearing a lot about these new and innovative ways to discover new quasars, but I just wanted to throw back to the early days of the quasar revolution. Beginning with things like SDSS, suddenly we had this huge population of these rare radiolab quasars at redshifts greater than 5 that let us do these really cool environment studies. And even those, dating back already 15 years, we found filamentary clustering of Lyman alpha emitters and massive red galaxies around redshift 5 quasars. And so once again, another shout out to Roberto's great paper from 2017, who found these C+ companions in redshift 6 to 7 quasars. So this is right at the end of reionization, and this overdensity of C+ emitters within 100 kiloparsecs of these quasars suggested these enhanced ISM luminosities at the same redshift, and possibly enhanced star formation less than a gigayear after the Big Bang. So my master's thesis led the continuum counterpart to this survey. So this is the same sample of 35 quasars between redshift 6 and 7 that were observed with ALMA band 6. And the hypothesis there is that dusty star-forming galaxies are rare enough that we expect less than one of them per ALMA primary beam. So if you find more than one continuum source within these small fields of view, that might indicate enhanced dust-obscured star formation. So I'm showing those same 4 quasars from Roberto's paper, where the squares are showing the C+ emitters and the circles are the continuum sources. So as you can see, we don't have spectroscopic confirmation of those continuum sources in these particular 4 quasars, and there were no C+ emitters in the others. So when we average over all 35 fields and compare to blank field number counts, on average, there's no continuum flux over density. And in 12 quasars, we found 15 total companions or sources in those primary beams, only one of them spectroscopically confirmed. So in this session, we've been talking about whether or not that is a real thing or an observational effect. And so earlier, we heard a little bit from Christina, like quantitatively talking about this, but here's my little cartoon of what it would look like to, look very far away at this quasar-centered protocluster. There are a number of things happening here. You're going to have a lot of objects that are at lower redshift, and depending on your sight line, you might be seeing a very dense, overdense filament or not. You could just be pointed away from it. So our survey possibilities with only 35 quasars, even though that's a relatively large sample compared to some other studies, we're still victim to cosmic variance there. And as amazing as ALMA is, it has a small field of view. So you're only looking at the inner 100 kiloparsecs, whereas I said that we need to look on megaparsec scales for these overdensities to come through. But the biggest thing with the continuum only survey is this large cosmic volume that you probe. And because of the strong negative K correction at 1 millimeter, you're going to be dominated by sources that are at redshift 1 or 2, and they're going to be at the same flux density as something at redshift 6. So that continuum signal might be washed out.
2 minutes.
I'm sensing a 2-minute warning. Okay. Physically, I'm actually excited to say these things because I've never been sure if these are like insane suggestions, but if the early universe is dust poor, then we might not see the overdensities in the form of, these dust continuum overdensities. And if quasar feedback plays an important role, then again, we're looking too close in. And finally, as Roderik suggested, quasars might not actually sit at the virial center of the overdensity. If they behave more like an embedded AGN along some random filament, then the study isn't going to find what we expect. So in my current project, we are searching for another population of galaxies in the form of LBGs. So we can constrain these a little bit better with broadband photometry and find potentially enhanced unobscured star formation. So these are the filters we have for 3 of the quasars who did show more than one ALMA continuum source. So we're shrinking delta Z by a lot, still not spectroscopic confirmation, but allows us to characterize the environment a little bit better. And the other cool thing is that we have the parallel fields with HST. And so that could either be an interesting control sample to compare to if it mimics the field, or if we find the overdensities there, then that could be evidence for these very extended filaments. And so here I am showing one particular quasar at redshift 6.8, where we are imposing the same color cuts that are used for the blank field UV luminosity functions at redshift 6 and 7, with an example dropout on the bottom there. And you can see that many of them do fall into this expected color space where the colored lines are showing, LBG evolution for different UV beta slopes. So there are potential sources of contamination and uncertainty there, especially if you allow that sample photometry to vary a little bit within the image noise. So this is still ongoing, but comparing to the blank field UV luminosity function with the same color criteria, we show possibly that things are the same as the field, except at the massive end of the luminosity function. So I'm going to have to wrap up soon, but this is encouraging evidence of potential enhancement only at the massive end, which might be predicted by SAMs. I don't know about that underdensity in the parallel fields. I'm not sure about that, but We know from simulations that brighter LBGs are more strongly clustered and in turn reside in more massive halos. So it could make sense that the enhancement would come in the form of massive galaxies. And UV luminosity function studies have found that the slope and peak of the redshift evolution of star-forming galaxies is different for the faint and bright populations. So just eyeballing this super preliminarily, it shows that perhaps our quasar fields are above that relation. And so we are seeing something different about these environments. Here's a really quick teaser slide on something I would really like to discuss with anyone who's more knowledgeable about this, which is that SED fitting would be the best way to constrain the photometric redshifts of these sources. But there's a lot of uncertainty there too. But coming back to my summary, basically in millimeter continuum, we don't see a flux overdensity. With LBGs, there maybe could be an overdensity only at the massive end, but we need photometric redshifts. And eventually I would like to calculate that cross correlation that Christina was talking about, but that is still a work in progress. So sorry I went a little bit over time, but I will happily take those questions. Thank you.
Yeah, we're actually out of time, so I think let's have the questions on the Slack for this paper. Niel, if you could, if Jaclyn stopped sharing, and Niel, if you could share. Okay, we see your screen.
All good?
Yes, we see your screen and we hear you, so go ahead.
Very good, thanks. So today I would like to discuss some work that we've done and that we're continuing, which argues that general supermassive black hole growth in the universe depends actually rather little upon the 0.1 to 10 megaparsec cosmic environment. The collaborators on this work are listed here. In particular, I'd like to highlight the work of Guang Yang, who was an excellent Penn State PhD student who led this work. Our overall approach in this study is to utilize a very well-studied sample of AGNs and galaxies so that we can perform direct partial correlation testing of the issue in question, and importantly, while controlling for other correlates of black hole growth, which we think is a critically important point. As you would expect from the authors, we use X-ray emission to measure black hole growth. We think that's a good way to go because X-ray emission is nearly universal from growing supermassive black holes. It can find the highly obscured systems, and it can also find lower luminosity systems because it doesn't suffer so much from host galaxy dilution. So we have known for a long time, of course, that the environment affects galaxy evolution broadly via mergers, tidal interactions, ram pressure stripping, cold gas flow through filaments, and so on. And of course, these processes might plausibly also affect supermassive black hole growth, because that, of course, depends on the cold gas supply. However, the great challenge in these studies is you must disentangle environmental versus other effects upon black hole growth. In particular, I want to point out that black hole growth strongly depends upon stellar mass. Here is a plot from another of Guang's papers, which shows the long-term average black hole accretion rate, again, measured via the X-ray techniques, versus stellar mass. And you can see there are order of magnitude level dependencies upon stellar mass. And so because, of course, we know that stellar mass itself is linked with environment, if you can't disentangle the effect of stellar mass and environment, any apparent effect upon environment might simply be due to the fact that more massive galaxies tend to like to live in richer environments. So we try to address this with direct partial correlation analysis, but this is a very challenging issue. It requires a large sample of very well characterized galaxies and AGNs in a region with excellent cosmic structure measurements. And there are only a couple, and arguably only one field on the sky where this could even be attempted right now, and that is the Ultra Vista region of cosmos. In this field, which is large enough to get somewhat of a sampling of cosmic structures, I'll say more about that in a minute, Darvish et al. Has done extensive studies of the structure and has resolved the structure both on 0.1 to 1 megaparsec scales and on 1 to 10 megaparsec scales into 310 redshift slices spanning a wide range of redshift where he does two-dimensional derivations of environment. This is done both with measurements of the surface density field with this delta parameter, as well as using a multi-scale morphology filter algorithm. And in Cosmos, then we are utilizing 170,000 galaxies containing 2019 X-ray AGNs. We estimate stellar masses for these galaxies using the extensive Cosmos photometric data via SED fitting with Segal. And this Cosmos allows us to probe environments ranging from field environments up to halo masses of about 10 to the 14 solar mass clusters. And those environments contain about 95% of the galaxies in the universe. And so we are getting the majority galaxy populations in the universe in this study, although we do not sample the rare, richest clusters in the universe. We again get the X-ray, use the X-ray emission to derive the long-term black hole accretion rate. The way we do that very briefly is we treat Cosmos as a kind of statistical sampling of the types of galaxies that tend to grow their black holes. That is, we take black hole growth to be ergodic. We can thereby average over samples of a given stellar mass, samples of a given environment to get a time average black hole accretion rate. And we do that using both the direct X-ray detection and stacking techniques. The quick summary of our results are here. First of all, we find that cosmic environment effects are small once you control for stellar mass. You can see that here. Here is the long-term black hole accretion rate in 3 redshift bins versus stellar mass. And then the color data points show the effect of splitting up the samples by environment into the denser environments on 0.1 to 1 megaparsec scales and lower density environments as the blue points. And you can see there's little splitting of the relation depending upon environment. And that holds true even if you select the sort of 20% least rich environments and the 80% most rich environments. The splitting doesn't really depend upon your choice of how you do the splits. But the same thing applies on 1 to 10 megaparsec scales, as you can see here. Here we split things into field, filament, and cluster environments, and there's little residual dependence upon environment once you control for stellar mass. Of course, the real quantitative way we assess that is with partial correlation testing. This table shows the partial correlation results. The end result is no matter what partial correlation method you use, and no matter what redshift you consider, stellar mass resoundingly beats overdensity. There is no detectable overdensity dependence after you control for stellar mass, as you can see from these low sigma values. These plots here, yes, okay, yeah, I'm almost done. These plots here show the residuals from the partial correlations. A pure mass model explains the data very well. A pure overdensity model leaves large systematic residuals. And so given these results, a couple of points I want to make. First of all, you might imagine there could still be subtler effects upon environment. That may be true, but if anyone wants to claim a subtler environmental effect, you're going to have to remember that, of course, we can't measure stellar mass arbitrarily well. And given that there is clearly a strong dependence upon stellar mass, any residual environmental effects might be simply due to uncertainties in the stellar mass. And of course, I will note that there could be effects upon black hole accretion rate in more massive systems, which we cannot sample with Cosmos. And indeed, there's interesting evidence there and interesting debate. I will just end by saying a few words about future prospects. We are very excited about extending this work into more fields. We are pushing into the deep drilling fields of the Rubin Observatory. And we have recently obtained a very large 5 megasecond XMM Newton survey of substantial parts of 3 of the deep drilling fields. Here are our new XMM Newton data. And with these, we will now have, in addition to Cosmos, 4 widely separated fields to explore this issue, to explore a wider range of cosmic environments, to minimize cosmic variance, and so on. And I'll wrap up there. Thanks.
Okay, we have a couple minutes, more than a couple minutes for questions. So we have a question from Girish Kulkarni. How should we reconcile these results with the clustering measurements that we heard about earlier today?
Okay, good. So a couple of things there. Many of the clustering measurements, if you're going to do these clustering measurements, my point again is that you have to control for stellar mass. I am not surprised that you find quasars living in rich environments, because more massive galaxies tend to live in those environments. And so the question isn't, is that effect occurring? It is occurring. The question is why? Is it truly something about the environment itself, or is it simply due to the fact that massive galaxies like to live in rich environments? These partial correlation results, which I have shown here, strongly indicate that it's just stellar mass that's driving things as far as we can measure it right now. Okay, that's the first point I'm trying to make with respect to that. And then regarding clustering analyses, there have been clustering analyses, particularly some of the more recent ones, that do now seem to do a pretty good job controlling for stellar mass. There's a recent paper by Krishnan et al., which investigates via clustering approaches, which is complementary to our partial correlation approaches in Cosmos and UDS, and they actually find quite consistent results with us. And if you look at the clustering results overall in Cosmos, there is a variety of results claimed, but on balance, I would argue they're actually fairly consistent, especially the more recent work with our findings.
Okay, any further questions? Let's see. Well, we're pretty much out of time. Real nice paper, Niel. Real
Thanks.
rigorous. I love that kind of stuff. Okay, so Taro Shimizu, if you could share your screen and okay, we see your screen, we see your presentation, and
Good. Can you hear me?
yes, go ahead.
Good. Thanks, Karen. Also, thank you to the organizers of the conference. So you might be wondering why my talk is being done in this session. We've been primarily talking on very, very large scales around quasars. And now I'm going to be narrowing down into the actual subparsec structure of AGN. Well, the reason is because I was supposed to give this talk on Monday, but thank you to the organizers of the conference for, on very short notice, being able to move my talk because I fell ill over the weekend. And so now I'm excited to give my talk today, even if it's sort of out of place from this session. And so I'm Taro Shimizu. I'm a postdoc at MPE and the IR group. And today I'm going to be giving you sort of a whirlwind highlight tour of what we've been doing with gravity, and then also future prospects with Gravity Plus on the subparsec structure of AGN. And so first, what is gravity? Gravity is the near-infrared interferometer at the VLTI shown here. And so it lives here in the VLTI lab. And what it's doing is combining the light from all 4 unit telescopes and producing interferometric fringes so that we can resolve structures on very, very small scales. So quickly, going through just a recap of just sort of the sort of smaller scale AGN structure. So it does expand out to several kiloparsecs. So out to sort of the narrow line region and ionization cone, polar dust, and we have instruments that we can resolve these structures very well, shown here. But what I want to focus in on is the so-called broadline region, as well as the near-infrared hot dust, which should at low redshifts occur on scales of 0.01 to 0.1 parsecs and 0.1 to 1 parsecs. And for this, right now, we need interferometry to help us look at these structures in a spatially resolved way. So with gravity, what we're doing for the broadline region is a technique called spectroastrometry. So I want to take you through this very quickly on how this works. So let's take 3C273 here. We have a broadline region sitting at the backdrop of our hot dust continuum in the K-band. And so now let's imagine the broadline region is, as we expect, a rotating disk of clouds. What that will do is cause a photocenter offset as a function of velocity. And what this produces is a phase difference in our interferometric fringes. And so if we look as a function of wavelength, the differential phase, then we get this S-shaped structure, because the differential phase is a function of both the line flux as well as the sort of photocenter offset. And so if the broadline region is a rotating disk, then we should get this S-shaped function in the differential phase curve. And so in 2018, we published our first observation with 3C273 of the Paschen alpha line. And that's exactly what we see. The differential phase has this nice S shape. And if we plot the photocenter offsets as a function of wavelength, it forms this very nice kinematic major axis, which nicely is perpendicular to the known jet axis. And so here we know for sure that what we have is a rotating disk. And so from this data, then we can also model the broadline region using a standard broadline region cloud model. and calculate or measure both the broadline region radius, here in this case is 46 micro arc seconds, as well as get an independent estimate of the black hole mass, 10 to the 8.41 in the case of 3C273. So now we've been able to, in the last couple of years, we've been able to do this through for several more AGN through the what I call the Gravity AGN project. This is the Gravity Large Program. And here we're studying 10 local AGN, not just the broadline region, but also as well as the hot dust and the coronal line region. And so here I just want to highlight across 3 papers for NGC 3783, IRS 09149, and then of course 3C273. We've been measuring the broadline region radius as well as their black hole masses, and we can start placing these galaxies on the known radius luminosity relation, which many people are aware of. This is then used in higher redshifts to get first order estimates of the black hole mass. And so what we're trying to do is to test, is this radius luminosity relation, independently test the existence of this radius luminosity relation in the local universe. And so far from our 3 measurements, that does seem to be the case, although 3C273 does lie off the relation, but that's also been seen in other high Eddington ratio AGN. Okay, now I mentioned not just the broadline region, but also hot dust. And so what we're doing here is both individual images of AGN as well as a survey across our whole program. And so here I want to highlight NGC 1068, where we've been able to spatially resolve the hot near-infrared hot dust. And what we find is this interesting ring, complex ring structure with a radius of about 0.24 parsecs, which is exactly the radius that you would expect for the dust sublimation temperature, which is where we would expect most of the near-infrared emission, continuum emission to be coming from. And so these clouds seem to be also co-spatial with the known maser emitting clouds, which we argue points to a sort of hot, thin, rotating disk of gas and dust near the sublimation radius that then is surrounded by thick molecular gas that's seen through observations like ALMA, that's several parsecs further out. Now, in our sort of survey, what we've done is double the sample of interferometrically measured hot dust sizes. And so here we're just measuring the visibility function as a function of spatial frequency and can get a Gaussian size. And what we find are larger sizes compared to continuum reverberation mapping that was also seen in previous interferometric observations with Keck and Amber. But we are starting to see a sort of luminosity dependence of the deviation of the interferometric sizes compared to the reverberation mapping relation. And this could suggest a change in the radial dust distribution. We have a accepted program to get 16 more dust sizes. And so we can really start doing a statistical analysis on the sort of luminosity dependence on the hot dust size. Now, what I also want to do is look to the future, and that's with Gravity Plus. And so I want to explain a little bit what Gravity Plus will do compared to Gravity as an instrument itself. And so there's several improvements that we're going to do over the next few years. One we've already done is a GRISM upgrade, so we have better sensitivity in the K-band. 2, very importantly, is we'll add wide field off-axis fringe tracking. So fringe tracking, think of it like an AO guide star that you need for adaptive optics measurements. Well, for interferometric measurements, you need a fringe tracker star. Right now, the limit is that the fringe tracker star has to be 2 arc seconds or less near your science target. And so that limits us to only the brightest AGN, because extragalactic sources, you're never going to find a star that's 2 arc seconds away. Now with a wide field off axis, we can go out to 30 arc seconds. And so we can really greatly expand the sky coverage. Now, also importantly, especially for faint AGN science, is we're going to completely upgrade the adaptive optics for VLTI on all 4 telescopes. And then also finally add laser guide stars to each of the unit telescopes. There's other performance improvements, including upgrading the vibration control, which will also further improve our sensitivity. So I want to mention that this is all PI'd by Frau Gasenhauer in our group, who also was PI of gravity. And so in terms of AGN science, as well as moving to high redshift, as I mentioned, our sensitivity, as well as our fringe tracking limit, as well as how close a star has to be, limits us to only the brightest and most nearby AGN. So something of the order of 10 to 15 AGN. Now, with these improvements to Gravity Plus, including moving the fringe tracking K-band limit, as well as allowing for wide angle off-axis tracking and improving the sensitivity, we can move to much higher redshift, all the way out to redshift 3. And so what is happening here is, number one, we're getting an improvement because BLR sizes should be bigger. So as they scale with luminosity, as we're going to higher luminosity quasars. As well as, if you remember from the differential phase signal, it's proportional to the strength of the line emission. And so as we redshift into something like H alpha at Z equals 2, our strength of emission greatly increases compared to what we had to use at low redshift, which is the Bragg gamma line. And so some science possibilities that we've outlined in sort of our phase A document, one that I'm particularly excited about is to trace supermassive black hole galaxy coevolution across sort of cosmic noon. And I think we can even push to Z equals 6 and 7. And so I was excited to see actually today Melanie's new paper showing the deviation in sort of the black hole mass versus stellar mass relations as a function of redshift. And so one of the exciting things I think we can do is actually start getting independent direct measurements of black hole mass at high redshift and test how the sort of known local scaling relations evolve as a function of redshift. Of course, with high spatial resolution, we can also do look at something like supermassive black hole dual AGN, as well as binaries, and there's a whole host of other things we can do. And so I just want to highlight phase 1 has already started for Gravity Plus. It's called Gravity Wide, which is this off-axis fringe tracking. And actually, in the last few weeks, we've been observing a redshift 2.3 quasar. That's just shown here in the acquisition camera image. It's a very small, faint blob. And here, this is the spectrum that we see on gravity. And so we're clearly detecting the strong H alpha line at redshift 2.3. And we've also detected fringes. There's analysis ongoing. And I just want to point out Gravity Wide will be expected to be available in the next ESO call for proposals. So in summary, I think Gravity has opened the door for high spatial resolution studies, the sub-parsec region around AGN. We've resolved the BR line region. We're resolving the hot dust continuum. We're testing local scaling relations for the radius luminosity relation. And then I think Gravity Plus has the potential to completely blow it wide open by pushing to much higher redshift, study supermassive black hole galaxy coevolution, supermassive black hole binaries, tidal disruption events, push out to Z equals 6, and there's a whole host of other science cases. Okay, thank you.
Okay, I've got to leave, and Roberto is going to take over. I got to go think about masses and springs. Bye.
Thank you very much, Tara, and thank you very much, Karen. So yes, we have time for a couple of quick questions. So I see there's one from Michael in the Q&A. It says really interesting stuff. What exactly is the radius of the BLR that you're measuring from the spectrostometry technique? The BLR likely to have a it has a final phrase. The BLR is not likely to have a sharp outer edge.
Right. So what we're modeling the BLR is distribution of clouds. And so our BLR for us is the, how was it phrased? The distribution is defined by a mean. And so it's this mean broadline region radius. In effect, we're measuring as the sort of the light weighted mean radius.
Okay. All right, thank you. Are there any further questions for Taro? All No, I don't see anybody raising their hand. So if not, then I think we're actually a little bit over time for the end of the session, so we can probably stop here. But if you have any further questions, we definitely keep asking them on the Slack. And thank you very much to all of the speakers of this session. Thank you very much. We'll take a break now, and we'll be back at 12:20 Eastern time, so about 15 minutes from now.